Okay, the final concept that we want to introduce is something called the gamma function. So the notation for the gamma function is capital gamma, and here's a formula to define it. Capital gamma of r, this is going to be defined for r positive. So for any positive number r, gamma of r is the integral from 0 to infinity of e to the negative u times u to the r minus 1 du. This improper integral is convergent for every r positive, and that's going to give you a number. And that's the definition of the gamma function. Now, if you were to look at gamma of r plus 1, you have this integral, and I'm not going to go through the details. You can look in the book for this, but if you apply integration by parts, you would find that gamma of r plus 1 would reduce to r times gamma of r. And that's a very useful formula for us to calculate values of the gamma function. Another thing that we need to use a lot is, what is gamma of 1? Well, that's when r is 1, then you have the integral from 0 to infinity, e to the negative u times u to the 0, or 1. That integral you calculate very easily, and you get 1. So gamma of 1 is 1. If I combine those two rules, then gamma of 2, well, I can write 2 as 1 plus 1. So it's 1 times gamma of 1. Gamma of 1 is 1, so gamma of 2 is 1. Gamma of 3, I can write 3 as 2 plus 1. So that equals 2 times gamma of 2. Gamma of 2 is 1, so this is 2 times 1. Gamma of 4 is gamma of 3 plus 1, which is 3 times gamma of 3. So it's 3 times, but gamma of 3 is 2 times 1. And this pattern continues. Gamma of 5 is going to be 4 times 3 times 2 times 1. In other words, gamma of n plus 1 is just n factorial if n is an integer. So the gamma function can be thought of as an extension of the factorial function. Factorial, it only makes sense to apply that to an integer, whereas gamma, you can apply it to any positive real number. Let's see here. One more thing that you can use. I'm not going to go over deriving it, but you can also use the fact, and you will need to use the fact, that gamma of 1/2 is equal to the square root of pi. And this is not beyond what you can do or what you could understand. If you look in the book, there's an exercise outlining how to derive that. Where did they say it? I've lost my page. Problem 26. So 7.7.26 is an exercise on how to derive this fact that the gamma of 1/2 is equal to root pi. Okay, now let's use this to get one more general rule about Laplace transforms. Let's take any r bigger than -1. And let's try to get the Laplace transform of t to the r. Now, we know what that is when r is a non-negative integer. We have that already. But here now r can be any real number bigger than -1. Okay, if I go to the definition of the Laplace transform, it's going to be the integral from 0 to infinity of e to the negative st times t to the r dt. And I'm going to make a u substitution. Okay, so u is going to be s times t. Okay, think of s as a constant. T is the variable of integration. So du is s dt. My integral now becomes the integral of e to the negative u, and then t is equal to u over s. So I have u over s to the r. dt is 1 over s, and I can put that outside the integral, 1 over s du. Okay, I change my limits of integration, so t equals 0 becomes u equals s times 0, which is still 0. And as long as s is positive, so we're also taking s positive here. When s is positive, then as t goes to infinity, u is also going to infinity, so my upper limit remains the same. Inside my integral, that s there, I can pull that out. So I'm pulling out an s to the r into the denominator. So outside I have 1 over s to the r plus 1. Then I have the integral from 0 to infinity of e to the negative u to the r, du. And then r, I can write that as r plus 1 minus 1. And then looking at that integral, you see that that is exactly gamma of r plus 1. So what we've just derived is this rule, that the Laplace transform of t to the r is equal to gamma of r plus 1 over s to the r plus 1. And that's true when r is bigger than negative 1. And that matches our earlier rule, because remember, when r is a positive integer, then gamma of r plus 1 is just r factorial. So this is an extension of our earlier rule that allows us to use fractional powers of t when we're doing Laplace transforms. Okay, so let's do an example of that. My f of t will be t to the 3/2 times e to the 2t, and I want to find the Laplace transform capital F. Okay, so first let's deal with the e to the 2t part later. The first thing I want to do is figure out the Laplace transform of t to the 3/2. Okay, so the Laplace transform of t to the 3/2, according to the formula we just had, is gamma of 5/2 over s to the 5/2. So I need to figure out what is gamma of 5/2. Well, I can just reduce it by 1 at a time to get first 3/2 times gamma of 3/2. And gamma of 3/2, what's that? That's going to be 1/2 times gamma of 1/2. And gamma of 1/2 is the square root of pi. So gamma of 5/2 is 3/2 times 1/2 times the square root of pi. So it's 3 root pi over 4. Okay, so the Laplace transform of t to the 3/2 is 3 root pi over 4 times s to the 5/2. Now the function that I was given in this example is that same thing, but multiplied by e to the 2s. So I need to take that result that I just got and replace s with s minus 2. So capital F of s is 3 times the square root of pi over 4 times s minus 2 to the 5/2. Valid when s is bigger than 2. Okay. All right, that's the end of 7.7. Might as well start 7.8 on a new part. So I'll stop this video and we'll start another one.